Yes, so we're going to talk about refraction, but just to be clear, you think the Earth is a globe, right?
No, I don't. I honestly, I don't know what the shape of the Earth is, but I think there's a lot of evidence that it's not a globe.
All right. Do you think there's evidence for something else?
Absolutely. Well, yes, I do. And I think when you look at it the way that I'm looking at it, there's only one way to look at it. But on the flip side of that, do you think there's evidence for a globe? I absolutely think there's evidence for a globe, especially when you look at the sky and when you look at navigation and when you look at the great circle routes of airplanes and all of the things that we observe. They work on a globe, and any flat Earth model that is going to work is going to have to incorporate all those things pretty much the way that we understand them, except for Earth curvature.
Well, I mean, we'll set that aside because, of course, it's measured. But, um, I mean, flat earthers have had 2,500 years to incorporate these things, and these things have been they're progressively added on as more things as we do more things. Right? We didn't used to fly around 200 years ago, but somewhere around 100 years ago, we started flying. So
So
great circle navigation in an airplane became a thing, and yet there were flat earthers at the time when the Wright brothers were going, did not incorporate an answer for that navigation. The well, so you take issue with the measurements of curvature,
mm,
um, and that goes right into refraction because typically flat earthers, when they do attempt to test, they'd say they're testing the globe. They set up a false dichotomy. They're like, if this test fails, then the conclusion must be the other way. But no, if that's not the case. The false dichotomy is that, right? If the test fails, then the hypothesis is falsified. That's all you can say for it. You can't say that some other case has been established. Right? For that, you need the positive test for that, the actual measurements of that. So if it were to happen that you set up a hypothesis for the globe and then you test it, and if it was all done right, right,
mhm.
which I've never seen, but if it was all done right, then it did not support the hypothesis, the conclusion is only it doesn't support the hypothesis. You still need to go construct a test for flat Earth, a measurement to test a hypothesis for it, run that test and get a positive answer, confirming it so that it supports the hypothesis of the Earth being flat. But that's never happened. Flat Earthers never, to my knowledge, have done that. Right? Jaron tried, as an example of somebody that tried. They've a few have tried. I'll say that. But generally, they're trying to falsify the globe, and it's always a misunderstanding of it. But Jaron did try to do the actual confirming positive evidence for flat Earth, and it didn't work. Right? And he said there was stuff in the way. Okay, go repeat it. Go try it again. He didn't. But that was, I think, an okay. There's other ways, maybe better to do it, but it was an okay test to test of flat Earth.
Well, I mean, you've got so many factors to consider in that test. I mean, you've got the temperature layer of the water, you've got the temperature of the air, you've got the barometric pressure that night. What was, how much dust is in the air? I mean, there's so many things, especially when you're firing a laser at an
Dust,
angle.
dust.
It's absolutely, there's particles
I know,
throughout the
but
atmosphere.
dust.
And if this is your angle on a globe, okay, what happens to the angle of refraction over a flat Earth where you have even more atmosphere? You have even more density at the surface. So if I look at a building across a body of water, and I did the calculations earlier, I use GPT-4 now for calculations. I don't even use a calculator because it's very accurate. It tells you exactly what you need to do, exactly how to do it.
And then here's the final thing that you had mentioned, that ray of light comes in at a slightly different angle. And since it comes in at a slightly different angle, it appears higher than it is if there was no refraction. So that's how things, for example, could could be behind something, right? That
Absolutely.
if you see that curving light there, if something was in the way that would have blocked the non-curving light, well, it gets around the curving light and it appears higher. So, for example, the horizon, right? The curve of the water as you're looking at it, the thing behind the curve, if there was no refraction, can now be seen because of that refraction.
Right.
Okay, so to go back, we've got this one here where the light hits the ground, as you said, right? And then this is where it looks higher, as you said. Now, how much higher is the question? If it's still, if it's significantly below you because of the curve of the Earth, then it won't appear above you. It'll appear less significantly below you.
Right.
Right.
Well, it always, I mean, a lot of times it'll appear level to the horizon. You'll see the whole building. Sometimes you'll only see half of the building. You have super refraction. You have all of these terms that are associated with the globe model. And when I'm looking at it from a flat Earth perspective, so anything that is at or below my line of sight. So if I'm looking at a building that's on the horizon and I'm looking down at that building, or if I'm looking at the power lines across Lake Pontchartrain, when they meet my line of sight, that is where I'm going to see refraction cause those objects to bend down and into the water. But if we look at the tower at the other end, that's at a higher angle, where I'm having to look up at it, that tower is being stretched out. If you look at the top of that tower, it's being stretched out and up, and it's the same downward refraction that's happening, but one set of photons is hitting the ground before it hits my eye, and the other set of photons is hitting my eye from this angle, making that end object actually appear higher because it is at a higher angle.
But now this won't cause things to be stretched. This will actually cause things to be compressed, because you're actually seeing more things in the same vertical space than you would if there was no refraction. So the building that would normally be non-refracted, blocked by the horizon, if now you see more of it or all of it, well, you don't have any extra vertical space to stick it into, so it all has to get squished, so everything gets compressed together.
Well, I think it looks like it's being stretched out, and I agree with you on that. But when you're thinking about refraction, you also have like inferior mirages, and you have things that happen in the upper when you're looking up at an angle, or when you're looking above the horizon.
Those are complications that really mess up observations, and so like sometimes it's caused by reflection, sometimes it's caused by ducting, sometimes it's caused by different layers that are different temperatures, and it's doing weird things in between there. So if there's ever those types of conditions, that's the kind of things where the conditions where you should not be drawing conclusions. You should say, all right, well, we're seeing refraction, we're seeing mirages.
Can I say something real quick about along those same lines?
Finish my sentence, then you say, all right, let's go somewhere else, come back, different day, do something. We cannot draw a conclusion from this because it's such a mess. All right, go ahead.
So how can we draw conclusions with what we're told about what we're seeing with the assumption of the Earth being a globe? Because when we make the observation, it's not like we can make the observation like with Lake Pontchartrain. What makes it unique is you can see the lines that are connected together, and exactly when that effect is taking place, you can see your line of sight, you can see those towers bending down into the water, and you can look at it through every step of the journey and see it. But when you're told something like, for example, well, refraction can't stretch objects, what basis do you have to believe something like that? Is it something you read? What basis does that article have to say something like that? And a lot of times in the scientific establishment, what I find is you have an explanation, but you don't really have the mathematics to back it up.
What the fuck? To see the roof of a building, you'd have to be higher than the building, right? So if let's say you're 10 meters above the ground and it's a 30-meter building, well, it's 20 meters taller than you are, so you're not going to expect to see the building. But if the building is 30 meters and you are at 30 meters, then maybe you could see a little bit of it,
but
right?
it would look like I was
but you'd
viewing
have
it at a higher angle.
but you'd need
If
yeah, but you'd need to
photons were
have an
coming off this
observation for
way,
that.
well,
But
that's the thing is how are you? That's the thing. How do you quantify these things without faith, Michael? Like, how do you quantify what the light is going to do over a surface of 3 miles
right here,
without believing that it's doing what it's
this
doing?
paper, this isn't faith. This is
But
this is
this
actual
is
empirical
assuming a
measurements.
globe. It's
Okay.
assuming a globe.
It's quantifying the amount of bending in the radius. So that bending the radius of the arc of curve is related to the radius of the globe, but you could just say, forget that. It's just related to this number.
What is the refractive index of air?
It's 1.0001.
It's 0.004 or something like that.
Yeah, it varies though. It varies a lot.
But okay, so we're talking about that variance, right? But when we're talking about the refractive index of air, you have to be able to explain that variance, and you're doing so with the assumption that the ground is curved in front of you in all directions.
But you are free to rerun the math without that. Like I said,
well, I have.
So what this is doing here, when it says -4 to +16, all this is reporting is the radius of the arc of light. So there's no horizon measurement. There's no horizon measurement.
Okay, even a point in the middle, even something before the actual horizon on a flat Earth, the horizon is thousands of miles away from me in every direction. I mean, there is no horizon. The atmosphere causes the horizon. And we can see that, on foggy days, your horizon, wherever it is, will change significantly. If it's high humidity, your horizon is going to be a lot different. I live here in Oklahoma City, or outside of Oklahoma City, and I can see the Devon Tower from where I live. On some days, I can't see the Devon Tower at all. On other days, the Devon Tower looks like it shrunk. And on other days, you can see the entire Devon Tower. It sits behind a hill, but you can tell by how far it's sticking above the horizon and the structure of the building that's behind the hill that you can't see, and know the hill's not curvature, but it's variable, and it varies. So my argument is that on a standard day, if we're looking on a flat surface, there's always going to be apparent curvature in the distance because of refraction, because the Earth is flat, right? The light, no matter what you're looking at over distance, the taller it is, the longer it's going to take to hit the ground. But over distance on a flat surface, all of that light is going to hit the ground. It could even be, if you're looking at this refraction right here,
wait, Chris,
and a difference.
Not all of it, because the light goes out, it splays out in all directions, so only some of it.
Right, the light going up, right.
The stuff that started at the correct angle to be refracted into your eye won't.
Right. Parallel or like this. So if you imagine rays going out, it would be the rays that are at or below. So parallel or below that, those rays are going to hit the ground over distance. So if you're looking at a building, the rays are coming parallel to your eyes. If you're looking at the sun and you look at the shadow of the shadow of the sun falls in one direction, the rays are parallel to the ground to your eyes from the sun that is lower than in most cases, unless you're 3 foot tall. But yeah, I mean, it's the reverse way to look at it, right? It's taking the globe and it's flipping it on its head and saying, well, what would it be if the Earth was flat? And it would work completely differently, but we would get the same results.
It would work completely differently, but you'd get the same results. That doesn't make sense, Chris.
Well, yeah, in one case, the Earth is flat, so the light is hitting the ground. In the other case, the Earth is a sphere, so the light is bending down over the surface. But it's going to work differently over a flat Earth, obviously. The light's going to do the same thing, but it's traveling over a flat surface instead of over a sphere. And you'll get the same result either way. Right? It's like a big wall of light that is just shining. That's why equinox, if you look at the graphics for equinox, they show these parallel rays coming from an 860,000 mile diameter sun. When you look at the diagrams for the eclipse, it shows the sun putting these rays into the moon and creating an umbra and a preumbra, and explaining it in a completely different way. And there's got to be congruency. It's got to be one way or the other. It can't work both ways.
No, it totally works both ways. All of the people that really studied this and understand the math and spent years and years and years on this, you're not the one that came up with the hole that they all missed.
No.
Okay.
But I am the one who comes up with the graph, or not the one. I mean, these are shared among all of us. I mean, we know the graphics. We've seen the memes, dude. I mean, this is nothing new to you.
I'm
Well, if it's
guessing
an
at
hour
that.
and a half after sunset and I can see the sun, that's 22 and a half degrees.
No, you're true. That's
I
true.
mean, that's pretty
You
significant.
don't see the
It's a
sun.
pretty big band.
You see the light coming through the air, right?
Yeah, but you don't, and this is what I'm saying. If you take a flashlight and you shine it on a ball, you're always going to get that perfect shadow around the edge of that terminator. There's no way to get that light to wrap around the edge of that
Because
ball.
that
It doesn't
ball
matter how
doesn't
big
have
your flashlight
because that
is,
ball doesn't have an atmosphere, Chris.
an atmosphere. Right. Okay, so this is where I was going with the perpetual sunset. So our observation of a lunar eclipse is explaining a lunar eclipse as Rayleigh scattering, or the light coming around the edge of Earth and illuminating the moon with this red light.
Okay,
But
yeah.
let's think about it logically. So the Earth in the sky of the moon is 4 times bigger than the sun, right? During a lunar eclipse, the sun perfectly matches
the Earth is
the
4
moon.
times. Wait, what's 4
In
times
the
larger?
sky of the moon, in the sky of the moon, the Earth is 4 times larger than the sun. It's 2 degrees. The sun is still relatively 0.5 degrees.
Okay.
Right. So it's 4 times larger. You can fit 9 moons inside of that diameter of Earth. And you're telling me that when Earth blocks it, you're getting all of this sunlight coming around the edge, making this red circle that's shining on the moon. It's illogical and it's stupid. For one,
Chris,
we have a black shadow on Earth with an eclipse from the moon.
Chris, just for reference, like I said, all of the people that have been studying this, you didn't just find something they missed. I want you to really ponder that for a second,
Michael, because it's got to match the model. So
it
show
does.
me a
Hold
picture
on.
of Rayleigh scattering around the edge of Earth.
Stop. It does, and showing you a picture.
Evidence?
Stop. Hold on. Showing you a picture is the simplified version. Do the actual algebra and trigonometry for it. Then
you can do algebra and trigonometry. I sent you the math for the 5th dimension with 10 rotational axes, right? Not the math, but the framework for the math. Now, what you're saying is this math, you're accepting it with faith and saying, based on math, I should see the light of the sun around the edges of Earth when the Earth is 4 times bigger than the sun in the sky of the moon. I mean, that's just ridiculous.
Okay. So Chris, I want to remind you, you're like, show me a picture. A picture is a simplified thing, right? And typically a picture is something that you put, the reason why somebody would make a picture, a not to scale picture of how the sun casts a smaller shadow on the Earth. It's not to scale, of course. And the reason why you would do that is to simplify it for somebody that doesn't grasp the concept yet. Because if the sun on a piece of paper is anything more than just a dot, right? The Earth is still just a dot. The moon is just a dot. They're so small compared to the sun, so you can't draw these things to scale. NASA has
pictures of this. They have pictures of it from the 60s, and it's really blurry, but it shows the little bitty Earth and being blocking the sun, but it shows the corona of the sun around the Earth. And it's the most ridiculous thing I've ever seen when you lay out the basic math. And back in the day, they didn't think about the math as much as they probably should have, because there are a lot of questions that we can ask.
Where it was this, first of all, NASA does put things out that are illustrations. So was this an illustration? And they note the things that are illustrations.
So here's an interesting question. This is an observation that I did make the other day, the Perseid meteor shower. So I was interested to see when the earliest observation of the Perseid meteor shower was. And according to the internet and GPT again, the earliest observation was 36 AD in China. So I did the math on that, just thinking about it as far as the precession of equinoxes, how the cosmos or the constellations kind of turn. This is why Polaris moves in the heliocentric model isn't always the North Star. But when you calculate this precession of equinoxes, it should have moved by more than 28 degrees, which is almost a full month. So in 36 AD, they were seeing the Perseid meteor showers on August 10th. And this year, it peaked on August 13th. So the peak after 2,000 years. And if you think about a comet like Tempel-Tuttle, it's not coming in on the ecliptic parallel to the ecliptic in line with the orbital plane of Earth, right? in the heliocentric model, Temple Tuttle is doing this. This is the ecliptic. Temple Tuttle is coming into the ecliptic and out of the ecliptic from above. So you would have to have an immensely wide comet tail that with a comet like that, and for it to be on the same day, that's an impossibility. The peak would not be on the same day after the rotation because it's been 2,000 years. And the cosmos should have rotated unless it's not moving like they say it's moving. And you really can't measure it unless you have faith in the NASA models and other space agencies. And yeah, they all work together. Absolutely.
All right. I want to remind you again, we've got Eric Burns is in the chat, and his mind is exploding because he is an astronomer.
Good. Let's hear his explanation.
So I want to stress this again, Chris. Astronomers didn't invent this to fool people, because the other astronomers that would come into it would be like, what the crap? That doesn't make sense. Because this is the thing they do. So you aren't the one that figured out the hole. They didn't
invent the Perseid meteor shower. God did. God figured it out, and nobody is pointing this out. So I would love the explanation from the astronomer for why I'm seeing the Perseids on the exact same days 2,000 years later.
Right. Instead of just kind of having some scribblings or some stuff in your head, write it down. Right. And if you look at the history of science, centuries of people writing down what they discovered, writing down their ideas, and sending it out to other people to say, what do you think? And the reason why you write it down is because it's coherent, it's together. It forces you to put together and to draw to some conclusion, to actually, if there's math that it does, that's involved, you put the math on the paper. And if you're like, I checked it myself, somebody else can come along and say, oh, let me check it too. So far, it's ChatGPT doing the math.
But no, because the math for refraction, bullcrap. I can do the refraction calculations for whatever you want. And the refraction calculations are what they are. So if you're saying they're that for a globe, they're also that for a flat Earth, because the surface isn't going to change refraction.
Yes, the radius of the arc won't change. Globe or
right,
flat. The radius of the arc of the curving light won't change. So the thing is, if the Earth were flat, then nothing could ever appear below. Unless you're really close to the edge, nothing would appear significantly below zero as your baseline for the no refraction condition.
See, okay, and then so refraction, the baseline on a flat Earth is refraction.
Let me finish my sentence. But let me finish my sentence. No refraction, right? Unless you're really close to the edge, right? If there's water spilling over it. The old style model. I generally, nobody believes that, but if you're really close to that, then there would be a dip. But if you're anywhere, marginally far away from that, then the horizon, no refraction, would always be right at zero, and just a minuscule, like 0.01001 whatever degrees below it, right? So essentially zero. But then you add in refraction, it will cause all of that to appear slightly higher. So everything needs to be slightly higher than zero.
It will not cause things to appear higher on a flat Earth. On a globe, it will if things are bending down over the curvature. On a flat Earth, you have the same angle, and the same angle is going to hit the ground over distance. The photons at the bottom of the object are going to hit the ground first,
yes,
making it appear to disappear from the bottom up.
That's not how it works. That's not how any of this works.
Level to the horizon that's there.
That's not how
it would look. That is why. What do you mean it's not how it would work?
That's not how it would look.
Because the horizon is in front of me. Yes, it is how it would look. The horizon is in front of me. The building is here. And over distance, if I'm this far away, I don't have any graphics on me right now. It's hard to explain. But based on distance, if I'm this far away, and the light is hitting my eye, the building's going to look higher, right? Look, light is hitting my eye, building's going to look higher. Light is hitting my shoes, not going to see the bottom of the building.
You still see the bottom, because the light at the bottom of the building doesn't just go straight. It comes up. There's light that went up at an angle. It gets to your eye.
Again, if I'm getting light from a higher angle, it will look like the building is from a higher angle. even if I change my perspective to a building by 10 feet, the building's going to look completely differently because I'm looking at it from a different angle. And that is clearly not what's happening when we're seeing objects across a body of water or anything else from 30 miles away. And the angular size of those objects must be taken into consideration, and it never is. I believe in orbit. I have an explanation for orbit. I have an explanation for geostationary orbit. I have an explanation for orbital mechanics. I mean, ask and I'd be happy to explain it to you.
All right, explain orbit.
Okay, so the ISS is a velocity vector that is perpendicular to the acceleration vector of gravity. So gravity is an acceleration vector that is pointing to the ground because the mass of the flat Earth is equally distributed below the Earth. Gravity acts the same way. It's a creation made by God, right? So let's think about it in slower terms. So let's think about a plane in the atmosphere of Earth. If the gravity vector is pulling the plane straight down as the plane travels, the plane, when it shuts off its engines, would fall straight to the ground. But actually what's happening is because of the velocity of the plane, that gravity vector is being stretched, right? Look at the shape of that. So the faster I go, so if I shut off the engines, listen, if I shut off the engines, I'm going to fall to the ground in an arc, right? And the closer I get to the ground, the more drag there is, the more this gravity vector is going to line up. At the altitude...
Wait, a plane flies because of lift.
No, at the altitude of the ISS, you don't need lift, right? So if I have a rocket that can get the ISS up to the altitude where I don't need lift, where there's very little friction, where there's nothing to slow the ISS down, how does the ISS gain altitude? It speeds up a little bit, right? So over time, it would be like launching a baseball into orbit, and eventually over 50 years, it's going to fall back to Earth, right, in the heliocentric model.
Yeah.
But if we're thinking about the ISS with zero drag traveling at 17,500 miles per hour, which is actually 16,000. And I think about that gravity vector that's pulling this way, it's going to break. It's like a rubber band, right? But if I think about orbit, so let's say I want to take a trip to the moon. If I think about orbital mechanics, I'm going to take the transfer orbit like this, and I'm going to go out to the moon at an angle that is more parallel to the vector of gravity, right? So when Kim Jong-un shot a rocket straight up 1,500 miles, when that rocket ran out of energy, it came straight back down to Earth about 30 or 45 minutes later, landed within a couple of 100 miles of where they launched it from, right? And that's because the gravity vector is pulling straight down. It's parallel, right, to these vectors of gravity. So if I want to achieve escape velocity is what it is, right? But we're not talking about escape velocity when we're stretching that vector based on speed, based on altitude, based on the fact that there's zero friction.
Why is the vector? But why is the gravity vector stretched based on speed?
Because let's imagine a baseball that we can propel at 500 miles per hour, and eventually that baseball is going to lose its energy, its forward momentum, and it's going to start to fall gradually. If gravity was pulling straight down, if that vector was pulling straight down on that ball would never launch in the first place, right? So think about walking. If I'm running and I trip, which I often do when I try to run, I'm going to fall on my face, right? I'm going to fall forward because I'm ahead of that. I still have that forward momentum. And if you imagine gravity pulling down, I mean, you can't make it be pulling straight down if you're moving 500 miles an hour across the surface because you're not going to fall. You're not going to fall straight down. You're going to fall based on the angle of that vector of gravity that's pulling you to the surface, and that is based on your speed. The way that I reconcile it, and I could be completely wrong. I find it very enjoyable to use my imagination and to come up with counter arguments about the globe model. I also find it that the Bible, the biblical model, to me is a flat earth model. And I'm very passionate about the book of Enoch. I'm very passionate about the scripture, but I don't know. And I'm not saying that if you don't believe what I believe about the earth, that God's going to judge you or anything like that. But I do think it makes life easier when you go through life with faith and when you recognize that there is a creator. Because here's the thing, this is why this argument's important to me. If the earth is what the Bible says, the only option is God in heaven. Right? There is no big bang if the earth is one-sided and resets in every direction. We are living in a program. We are living in what God made us to live in, and that's the earth that I believe we live on. And if God Michael, you're making fun, or not making fun of me, but you talk to me about extra dimensions and we laugh about it all the time. But where does God live? Right? Does God live on a star or a planet, or is he from another galaxy? Is God an alien, or is God beyond everything that he created? And if God is beyond everything that he created, the physical laws are what God makes them. We don't see the sky revolve around us because we're living on a globe.
All right. Well, I just have to say, if you're like, oh, if the Bible's right, well, here, the Geneva Bible from 1650 says he buildeth his spheres in the heaven and hath laid the foundations of his globe on the elements of the earth. He calleth the waters of the sea and powereth them upon the open earth. The Lord is his name. So you're like, hey, the Bible says globe right there.
It doesn't. The 1611 King James Version says flat earth. Or not 1611, but the one that came right before that. And this is a translation, right?
The 1611 does not say flat earth. Hold on.
It was the one before that.
Chris, there is no version of the Bible that says the earth is flat.
Not the Geneva. Yeah, it's the Geneva Bible, I think, that did.
No version of the Bible says the earth is flat.
Yeah, every version of the Bible says the earth is flat. The earth is laid out on 4 corners.
There is no version of the Bible
that
says the earth is flat.
Where did Jesus go to see all the kingdoms of the earth, Michael? Where did Jesus go?
It was figurative. There is no mountain high enough.
Oh, so what
is the name of that mountain that is in Israel that he was on? Let's go there today.
Oh, no. The name of that mountain is where Enoch was. Enoch said there was no firmament on that mountain. That when he looked up, it was dreadful.
Where is this mountain? You say this mountain exists.
It's not where we can go. It's where the devil is.
They call me a